Hello, my name is DJ Lewis and this is Lab 2, Observing the Motion of a Falling Object. Today I would like to talk to you through my experimental setup, models, results, and answer a what does it mean and what if question. The purpose of this lab was to observe the motion of an object that is dropped from rest and falls somewhat slowly, straight down. Somewhat slowly meaning more slowly than a rock dropped from rest from the same height. Also, I had to model that motion and graphically compare the observed and modeled motion using Newton's second law. I used Python to find the velocity and position of a paper plate dropped from rest. I found that a non-zero net force acted on the plate. Ultimately, I found that incorporating both the weight and drag force into the Python code used to model the plate's motion proved to be more accurate than just using the weight force in the model. So here's my experimental setup. By taping and folding a paper plate, I created the system for my experiment. First, I used my height to calibrate tracker. Next, I established my axis with the plate at the origin and the conventional down direction as the negative y direction. Then I cut the video down into the motion I was interested in, which was the object starting from rest and falling straight down. Finally, by tracking the point mass of the plate as it fell, tracker recorded the position of the plate over time, as you can see here in this graphical representation and chart representation. In order to create the computational model assuming the weight force equaled the net force, I started by assigning initial conditions. I looked online to find the average mass of a paper plate, which was 19 grams. The plate's initial position was derived from tracker, and the initial velocity was 0 because the system started at rest. Next, I assigned 9.8 to g for the magnitude of gravitational field near Earth's surface. J hat was given to us as the unit vector of the y-axis. With this, the weight force could be found using the equation W equals mg times j hat. I ran this code and Newton's second law predicted the motion of the plate assuming only the weight force acted on the plate. In order to add drag force as well, the fact that drag force is proportional to the magnitude of velocity squared was used. Therefore, I knew the drag force is equal to some constant b times the magnitude of velocity squared. B was found by choosing an arbitrary b, running the model, then looking at the printed final position. This process was repeated until my model matched with the last observed y position of negative 1.732 meters. B was found to be 0.00192. Next, I had to state that F net equals the drag force plus the weight force. Using this F net, Newton's second law found the velocity and position of the paper plate over time. And we can see Newton's second law right here. Vf equals Vi plus F net over mass times delta T. And Newton's law was also used to find the position here, which is the plate's final position equals the initial position plus average velocity times delta T. Arrows were also made to illustrate the forces acting on the plate. The weight force, depicted by the yellow arrow, remained constant over time, while the drag force, the blue arrow, increased over time as speed increased. So here are my results. As you can see here, both models fit fairly well with the observed motion. The weight force model underpredicted the position of the plate at the end because drag became more of a factor as speed increased. When drag was incorporated, we can see that the model lines up with the observed motion almost perfectly. This can be fixed by changing the drag constant b or slightly changing the video orientation. So now to answer this what does it mean question. The model with drag predicts a terminal velocity while the other does not. Terminal velocity is achieved when the drag force equals the weight force and the object has constant velocity. Therefore, drag must be present for terminal velocity to be achieved. So now for the what if question stated here. Terminal velocity will be reached faster because the drag force will be greater faster. This is because the magnitude of the drag force is proportional to the square of the object's speed. The faster the drag force increases in magnitude, the faster it will equal the weight force. Thus, terminal velocity can be achieved. Thank you for your time.